So this is a joint work with Ross and Ivanov from Dublin. And what I will try to explain in this, in my talk is that equatorial waves and the equatorial wave current interactions are quite interesting, and there is a lot of mathematical structure there that can be exploited and looked at. So let me first start with a few general comments about oceanography. I've been working in this area for a few years, and well, it is a very challenging area because you have many temporal and spatial scales. Ocean flows are unstable. Many currents are non-uniform in the sense not only that they change with depth, but they change direction, they change strength, and so forth. Fortunately, from the point of view of analysis, the computational problems, by what I mean by that is you can do numerical simulation, but it is not satisfactory because the system is too big and too complicated. So there is a need for analysis. There is a big data approach, very popular, but I think that many things, the fine things, are missed in this kind of approach. And the real problem from the point of view of an applied mathematician that looks at this, and from the point of view of someone working in analysis, is that there's a lot of ad hoc modeling. So a lot of papers are based on assumptions that, well, are mathematically maybe justifiable in the sense that you can apply your preferred method, but physically, why this and not something else, that remains to be seen. But there are a lot of opportunities in the sense that there are certain simplifications and certain regimes where there is a well-defined structure where you can hope to do nonlinear mathematics. So first of all, inviscid theory is important. So that's good. It's one simplification. There are regimes, for example, the equatorial one, where the structure of the ocean flow is fairly coherent. So you don't have huge instabilities. And there are regions like the equatorial where there are not too many factors to take into account. So the size is manageable. And one big advantage is there is an enormous amount of data that is available. So this could be an advantage, but also a disadvantage because in a sense, it's almost too much data. Right, so I'm going to talk mainly about the Pacific because there things become more evident. And I'm going to concentrate on a band about 300 kilometers centered on the equator. So it's about 1 degree to the north, 1.5 degrees to the north, and 1.5 degrees latitude to the south. That it stretches over 11,000 kilometers over the whole Pacific. And well, the good thing is that the bed is almost flat. So that's the flat bed assumption can be made. It's reasonable. Now, there is a stratification greater than anywhere else. There is a lower density fluid atop of something that is, atop means in the 300, 400 meters, and then you have a little bit more than 3 kilometers of practically motionless water. The other complication is that you have two currents. Well, there are two currents occurring. At the surface, you have a current that goes from America to Asia, because this is how the winds are blowing. So you have a current that is a wind-induced current in the upper 200, 300 meters, and it goes westward. Westward means towards Asia. But at depths just below this one, you have another current that goes from Asia that goes eastwards. And it was discovered quite late in the 50s, accidentally on a fishing expedition. And it goes at between 100 and 200 meters. Below 400 meters, there's not much going on. And so you have, it's like an interface where the two densities meet, and you have surface waves. So you have surface waves and waves at the interface, and there are currents. And there are big differences between the two waves, because at the surface, the waves are, it's gravity waves we are interested in. So it's 3-4 meter high. The ones at the thermocline, so at the interface between the denser and the less denser fluid, are much bigger, almost a factor of 10. And there's a difference in speed between the two. So they are different type of, they present different types of dynamical behavior. Okay, this is a little bit, well, an idea what is going on. So what you have is, along the equator, the wind is blowing practically only towards westwards. And what is drawn here is the surface current that is wind induced, and it goes westward. And as it happens, near South America, there is cool water, relatively cool, I mean cool for the equator. And near Indonesia and Australia, you have warmer water. This is at the surface. And this is another figure. The equatorial counter, well, these two currents, the North Equatorial and the South Equatorial, are further away, few hundred kilometers, so they will not affect the dynamics I'm talking about. And the one in the middle is not the surface current, is the one that goes at 100, 200 meters depth, and it goes from Australia towards South America. Right, and so what we have here is an inviscid two-layer fluid flow with non-zero vorticity. And actually a vorticity that changes sign, because I will be more specific in a moment. And it's in a rotating frame associated with, because the Earth is rotating around its polar axis. So the choice of coordinates, these are rotating coordinates. X is in the longitudinal direction, Y is latitude, and Z is the local vertical. And they are rotating. So because of the Earth's rotation, the forces that act other than gravity, there is the Coriolis force, because we want to write, to use Newton's law. So this comes up, this fictitious force. And it has this expression, phi is the latitude angle in the spherical coordinate system. Big omega is, this is the rate of rotation of the Earth. And we ignore centripetal terms because they are much smaller. And there is one important feature here which makes the analysis possible. The fact that the Coriolis force so when you put phi equals 0, you will see that, well, the sign becomes 0. So the meridional component is not there. And this makes the wave propagation to be east-west or west-east. So the fact that we are at the equator makes physically almost as if the equator were a wall, a vertical wall, and waves propagate along this wall in one direction. This is a big help because we don't have to deal with three-dimensional waves. It is two-dimensional waves within this little region, within this region of about 300 kilometers around it. And right, so the fact that there is a thermocline, so the fact that there is this clear stratification is specific for the equator. You don't find this is quite rare in other places. And the velocity component, so it's reasonable if you look at the data to take an inviscid, free boundary, two-dimensional fluid flow with stratification and vorticity effects. So I will write now, this is a figure explaining a little bit what the variables are. So this is a vertical cut, and the X, the bars are because these are physical variables. I will non-dimensionalize them. So whenever there is a bar over, that means it's a physical quantity. So U is meters per second, the surface is meters, and so forth. The density is the unit for density. So you have you have a free surface that oscillates much less than the thermocline or this interface. So the height is a factor of 10, much more than in this figure. H is the mean depth of the internal wave. So this is something like 3.6 kilometers, and H1, it's 100, 200, up to 300 meters is this surface layer. And you have a density ρ1 and a density ρ, and this is a stable situation. Ρ is bigger than ρ1. ρ1 is the warmer water, warmed by the sun. And the problem here is that, okay, there is a velocity field, everywhere, but because of this orientation of the currents, you have a surface current that goes westward and this equatorial undercurrent that goes eastwards. It is convenient to split the velocity field, to put a 1 for the one over the internal wave and without an index for the one below. And the same eta will be the interface, and eta1 is the free surface. And there is a flat bed at the depth minus h, where h is something like 4 kilometers. Right, so because the flow is inviscid, you have the Euler equation in the two layers. And there is the contribution here from the Coriolis force in this omega, encoded in the omega that is here at the equator, so you don't have cosine and sine because the sine is 0. It's the F-plane approximation, so cosine of the latitude is approximated by 1 and sine by 0. So you have this omega term here. Other than that, it's the standard Euler equations. There is a difference in the Euler equation. You have 1 over density on the right. Well, you can move it on the right hand side, and there is ρ1 and ρ, right? And the difference is not that big. It's a factor of, you see, it's like 4 per 1,000, but this still makes a big difference. So this is the notation. So the governing equations are the Euler equation. We have mass conservation in each of the, and now what are the boundary conditions? So at the free surface, eta1, you have that the pressure should be equal to atmospheric pressure. And you have the condition, this kinematic boundary condition about the W is the vertical velocity, U is the horizontal one, eta is the surface. So this is the kinematic condition telling you that the particle on the free surface will stay there. At the thermocline, because I did split the vector field, the velocity field into the upper part and the lower part, I write it twice, W1, U1, W and U. So the interface is a free bound, it's a boundary for the lower part and also for the upper part. So I have these two. You have continuity of the pressure across the thermocline, and at the flat bed there is the condition that the flat bed, that water does not, so this last condition here is the flat bed is impermeable. Okay, now because this is inviscid, normally this should be all conditions, but if you look at the data, you see that, so the normal boundary conditions are that at the interface, the pressure is constant and the normal components of the velocities. So you could have, within the inviscid setting, you could have the tangential ones to be discontinuous, but this is not the case here. It's in this context. So what we have an extra condition is this one here that I write, and this basically tells you that the tangential velocity is also continuous. So across this thermocline, there is a continuous transition of the velocity. As we will see, not more than this, it's not C1, but it is continuous. So the tangential and the normal coincide. I mean, it's a continuous, right? Now, about this non-uniform current. So the current can be defined as you take an average, or a horizontal average, and you define what did that mean is that represents the current, and then the waves are fluctuations around this. And just as a non-zero vorticity tells you that there is a non-uniform current, And there is one important observation, is that the energy tends to be concentrated in the lower frequencies. There is a difference in frequency between the surface wave and the internal wave. The internal wave is slower and has a much bigger wavelength, and this is the one that transports most of the energy. So it is, and the length of the internal waves in this context is several hundred kilometers. So we are measuring things in tens of kilometers. It depends. I mean, some texts in oceanography talk about wavelengths of 1,000 kilometers, but this is not very accurate. But in any case, the surface waves are a few hundred meters. It's like waves, normal waves at the sea, but the internal ones are measured in tens of kilometers, and these are the ones that will transport energy, and these are the ones that are larger. They are also slower, as it turns out, but this is right. So the first thing is, so we have to account for vorticity, because and there is a shear at the surface. The flow is westward. Somewhere at 200 meters depth it is eastward, and then it's still. So you cannot have uniform flow, you cannot have irrotational flow, so you have to have vorticity. And the simplest setting that would be realistic would be to have constant vorticity in each layer. Because at the top you need the shear the shear is different in the two, so you need at least two different values for the vorticity. So the simplest setting that would capture the essence would be constant vorticity on top, constant vorticity below the thermocline. And the advantage of constant vorticity is that it's this nonlinear flow separation, that you can, whenever you have constant vorticity, even in this two-layer setting, you can take the average, that defines the current, and then you have an irrotational wave perturbation on top. And this is without approximations. This is just because it's constant vorticity, and you can split. So for constant vorticity, you can split the flow field into a current, a pure current, and an irrotational wave perturbation of this at the level of full nonlinear theory without approximations. And this is helpful because we will see the details in a moment. So now this explains a little bit this current business. So what you have, what this is supposed to indicate is that above, so the pure current, there are no waves. So the free surface is Z equal H1. The thermocline is Z equals 0, because this is where most of the action happens, the important one. And above the thermocline, you have a current that goes to the west at the surface. And at the thermocline, you have a current that goes the other way. So the simplest way to capture this in a continuous way with a continuous velocity field, so a purely horizontal, so the vertical component is 0, but the horizontal one has to change direction, and it's this one. So it's a piecewise linear thing where gamma and gamma 1 arrange take care of the constant vorticity. The other thing I have to take care of is that at the bed, Z equal minus H, there is no flow, so U is 0. That explains the expression on the bottom for U. And then at the surface, U1 connects continuously at the thermocline with the eastward flow, and at the surface it points westward. And as indicated in the figure, the strength of the maximum at the thermocline, so the maximum is at the thermocline, and it's 3 times bigger than the absolute value of the minimum that is at the surface. So this is about the right size, and I take the orientation X is in the direction of the rotation of the Earth, so it is eastwards. And this is, so gamma is the one below, it's positive, gamma 1 is negative, is the one on top, and you have this thing that it's westwards, and at the thermocline is eastward, translates into these inequalities here for the two values of the constant vorticity and the two heights of the two layers. And well, one thing that is interesting here that shows you that this is quite different than the case of gravity waves. Why? Well, if you look at mass transport, so you just compute the averages of this and you take into account, then one will notice that there is an eastward mass transport. This is a little bit unusual for in the context of fluid, because if you make experiments in a wave tank, what you will observe is it tends to be, if you have mass transport by the waves, there is an undertow, there is a contrary mass flow at the bottom. This is not the case here. So the mass that is transported from west to east, because the mass transport here is eastward, it's not at great depths. There is no motion at great depths. Rather, it gets transported at a different latitude. So it is a different setting than just the one. So there are similarities, but there are also differences to the case of gravity waves. Right. So now all these equations were written in physical variables with these bars. And now I want to write them in a non-dimensional form in order to perform some analysis. So what do I want to do? Well, an inspiration for our approach was are several works by Catherine and Walter Craig about the Hamiltonian formulation. We are in a slightly different setting here, but what I want to convince you of is that these equations are quite complicated, but they have a very nice structure, a Hamiltonian structure, at the level or at the nonlinear level. And because they have this, you can then make approximations and derive model equations, simpler one, especially in the shallow water regime, where you can inherit from the original system this Hamiltonian structure. And not only inherit, but as is the case with gravity waves, where the Euler equations have a Hamiltonian formulation, Zaharov did this, and then Walter Craig and expanded upon it. So you have a Hamiltonian formulation, but when you go to models, go from shallow water nonlinear, weakly nonlinear models, you get KdV. So here, and KdV is more than integrable. It has two compatible Hamiltonian structure. It has infinitely many conservation laws. So you enhance the structure. You start with something nice and you can enhance the structure. And something similar is going on here. And this is what I want to, this is the aim of my talk, to show this. So to get there, first I have to non-dimensionalize the equation. So I think, okay, it's a length scale. I pick a length scale of 500 meters. Why 500 meters? Is because it is important here to capture the strength of the currents. So if I go to several kilometers, then this layer of 100 will be too small. So 500 meters is a good compromise to see the stratification, and also to see the stratification and to be able to talk of relatively long waves. Now, the reference for the velocity is 0.5 meter per second, because roughly this is the speed of at the surface of the current at the surface going westward, and 3 times this quantity is the internal one, the EUC, that goes at 100, 200 meters. So this is just to have a reference. And then, okay, the length scale, I use it for the vertical and the horizontal. For the vertical and horizontal velocities, I have this U bar. And then time, obviously, if I decided what the length scale is for distance and for speed, then time can only be that. Okay, and so if I don't write an overbar, this means these are non-dimensionalized quantities, are numbers, and I can work with them. And similarly, there is this non-dimensionalization of the depths of the 2 layers and of the 2 waves. Eta 1 is the surface wave, and eta is the internal wave, so the oscillation of the thermocline. And if you write it down, then this is the system that you get. So basically, this is in both cases, so with the U1, this is the one near the surface. It's the standard Euler system with this little omega being the non-dimensional version of the Coriolis or of the Coriolis parameter. Okay, this is mass conservation, and the fourth equation on top defines the value of the constant vorticity gamma 1. And below the thermocline, it's something similar. Because of the choice of the non-dimensionalization, what you have here, the density is slightly bigger. There is this little factor. Instead of 1, I have 1 plus r here that I have to divide with. Again, mass conservation and a different vorticity gamma. So these are the governing equations, and these are relative values of, so there is a little g here that accounts for gravity. It is, I mean, it doesn't matter what these values really are because I'm not going to do numerics or something, but just to have an indication of how they are. So gravity, you can see from the value of these, that gravity is quite important. It is very big in this scaling. Right, so, okay. So if you wonder what realistic values of these two vorticities are, they are written here in physical quantities. So one is negative, the other one is positive. Okay. So the boundary conditions in non-dimensional form are, well, the pressure is constant at the top. The non-dimensional constant now takes this form here. The second equation is the condition that the surface stays on, a particle stays on the surface. The next one is that the particle stays on the interface. There is a plus here that's an error here. That's a typo. This is because I did split into W1 and U1 and W and U, I write it twice, but the velocity field is continuous. So the third and fourth equation are basically the same. The pressure has to extend continuously between the two layers. Deep down, there is no inflow or outflow. And right, this is the equality of the, yeah, and the non-dimensional version of the currents are written down here. So basically what I have, this is the velocity field on top, and this is the current on the bottom, and what you see on the bottom is an average of what is on the top. This is this nonlinear. And now the advantage of constant vorticity is that, of course, it's not rotation, it's not irrotational, but, well, not too far off in the sense that mass conservation, so first of all, there is a stream function because you have mass conservation. So there's a stream function psi1 on top, a stream function psi for the layer below the thermocline. And because it's constant vorticity, you have Laplace of psi equal gamma below, and Laplace of psi1 is gamma 1 above it. And because this is constant, then you can easily see that there is something like there is a perturbed velocity potential. So in the sense that, right, what I'm looking for is, so I don't want to introduce things in the, if I write u minus gamma z plus h, that will be harmonic. And this is how I find the phi x and the phi z, okay? So psi and phi are not harmonic conjugates, but if you take out this quadratic expression from phi, you will make them harmonic conjugate. Now, how about, I mean, at the interface, what are the regularity properties that I have to account for? The stream functions are C1. So my assumption, based on the data that is available, was that the velocity field is continuous across this interface. That means that the stream functions, when you write down the expressions, you can convince yourself they are C1, they will not be C2. So psi and psi1 are psi and psi1 are a C1 extension of each other, but for phi, this is not even continuous. So one has to treat the two things somewhat separately. Now, the next thing that you can do for irrotational flow and also for constant vorticity is to write the Bernoulli equation. And basically, we have two Bernoulli equations, one above and one below the thermocline with slightly different gamma 1, and the density changes. So you see this 1 plus R below. So this is useful because you can recast the Euler equations with omega, with the Coriolis. You see the little omega in there, so this is not a problem. So the Bernoulli equation is useful because basically you can ignore the pressure from now on. You have this, so you reduce the number of unknowns. And what I want to do is I want to write this as a Hamiltonian system. So there has to be this Hamiltonian, and typically that's an energy. And if you look at what has been done for irrotational gravity waves, it should be the potential plus the kinetic energy. Now, the kind of flows I'm interested in are localized perturbations of these currents. So what I'm looking for, you have these currents and you have localized waves that perturb them. And so I want functions to be in the Schwarz class. Yeah, I want them to decay far out, and this is how I define localization. So I'm not in a periodic setting. So the first thing is this energy, whatever one decides that the energy should be, it should be a finite quantity. And the way to ensure this is so EK is the kinetic energy. What you do, U and V and U1 and V1 are the velocities. And when you take averages, you get the current. So what you do in order to get a finite kinetic energy, you take out the current component. So basically the energy is what the kinetic energy would be for the wave minus the corresponding for the pure current. And this is a finite quantity, and I do it in both layers, and the 1 plus R tells you that this is the layer deep down where the density is bigger. And the same for the potential, this is simpler. And the motivation for this is, first of all, you want to avoid infinite energy, and secondly, the motion takes place because all the time kinetic energy is transformed into potential, but not all the kinetic energy is transformed into potential because these currents remain basically unchanged. So it's only the pure current background state doesn't permit this transfer. It's just at the level of the waves. And this is another indication that this is how you should define the energy if you want to look for these localized wave perturbations of a pure current background state. So this is the Hamiltonian, and these are the, okay, so what are the variables now? And as I said, the inspiration for this work is the work of Zaharov from the 70s for deep water gravity waves, and then the subsequent work by Craig, Catherine, and others where these ideas were developed in other settings, irrotational flow, but with surface waves, internal waves, and also Hamiltonian derivation of Hamiltonian model equations. So the idea is the following. Maybe before I go through this text, okay. The constant vorticity is advantageous because I can split the velocity field into a pure current form and a wave perturbation. And this wave is harmonic, the wave perturbation. That's a great advantage. So it means that underlying I have this phi and similarly the phi 1 are harmonic functions. And so what one does is one takes the restriction, for example. So I start with the lower. Let me just go a few pages forward. I should have somewhere. Okay. So what is here? In order to simplify the equations in the sense, okay, I will have to pay a price, non-locality, but I reduce the number of variables. I reduce the number of variables by using the Dirichlet-Neumann operator. but I have to use two Dirichlet-Neumann operators. For the lower layer, I have a flat bed and just the interface, the internal wave. There it's simple because, okay, it's just, you take a Dirichlet condition on the thermocline, and you associate to this the Neumann, the normal derivative. That's one Dirichlet-Neumann operator. That's a scalar one. But then when you go to the upper layer, there you have two free boundaries, so to say. You have the interface, the thermocline, and you have the free surface. So what you have to deal here with is a matrix operator, because you have two conditions. You have a Dirichlet condition on the thermocline, another one on the surface, and you want two normal derivative, two outward normals at the flat, at the free surface and at the interface. So this is a matrix one. So for the upper part, you have a matrix operator. For the lower part, the fact that you have a flat bed simplifies things, and it's a scalar thing. So the advantage of this is that I don't have to write, for example, in the condition that the particle stays on the surface, in terms, I can define everything in terms of this operator and the trace of the, it's not the velocity potential, but it's this modified velocity potential on the interface. And the same there. So, right. So, well, then you have to, this is not enough. You have to take a combination. So basically, what is here, these are the two. So the Hamiltonian is, you get this sum of kinetic and potential energy that come purely from the waves. And the variables are eta, eta1. Eta and eta1 are the waves. So eta is the oscillation of the thermocline. Eta1 is the oscillation of the free surface. And then you have two other variables, psi and psi1. Now, these big phi, they are defined here. So phi1 and phi2 are the traces of the two velocity potentials on the interface, on the thermocline, and on the free surface. And this is how you define these two variables. And then, okay, in the L2 inner product, what you get, the main result is this one. The governing equations for constant vorticity on top and on bottom have this canonical Hamiltonian structure here. So it's a standard Hamiltonian system. The Hamiltonian operator is here, and it is for Schwartz class functions. Okay, and so this is the Hamiltonian structure of the governing equations. And now, just 1 minute, you can take the long wave approximation and you can derive approximate models. There are two wavy things, one at the surface, one at the interface. I'm more interested in the thermocline. So what you get, it's a KdV-like equation. The values of the constant don't matter. It's a mixture of the ratio of the two densities, gravity, gamma, gamma 1, something. But what you see here on top is a KdV equation where the only change in the coefficient, H1, and all of these things alter the coefficients. So it's a KdV equation. This is the shallow water evolution of the thermocline. In the shallow water regime that is written here, if you take steeper waves, then you get like a Burger's equation, which is here. This is again for the thermocline. And it is, I mean, there is data where they show that, I mean, they can keep track of soliton interactions at these internal waves. So it is not an accident that you get something like, so by soliton, I mean solitary waves that interact, keep their structure, and then they regroup according to speed and height. And they have seen trains like this for several, I mean, not just two waves, several waves they have been observed in recent years. So all these observations about nonlinear internal waves are not what are 10 in the last 10, 20 years. I think I went over my time with a few minutes. So that's the end of my talk. And the details are to be found in this, it's in the footnote here. You see this is a joint paper with even if there are a lot of technical details, it's a longer paper, but the basic ideas are, and motivation is what I try to explain in my presentation.